Um, okay, good morning, everybody. So we are Harlem Retrofit Lab Phase 4. So team members, I'm Joe, Maya, Monica, and then Rajvi is online. Advisor is Professor Bobker. We wanted to first give acknowledgement to what the Harlem Retrofit Lab is. So it's a continuation. So it's a community-based initiative focused on supporting building decarbonization, local on ISO compliance, and grid interactive technologies. Specifically, want to shout out Harlem Retrofit Lab 1, 2, and 3. 2 is specifically relevant to the first section of the work that I'll go over, which is the retrofit phases. Um, so our agenda today, we're going to go through Local Law 97, our energy improvement districts, our phase retrofit packages, envelope retrofit economic performance gap, and then what the EID is going to do. So first, Local Law 97, quick overview, very quick. New York City law that sets carbon emission limits for buildings over 25,000 square feet. The goal is to cut emissions by 80% in New York City. Compliance has already started, net zero goal by 2050. Majority of the time, it requires deep energy retrofits to achieve the 2050 goals, which is very difficult, as we'll see and go through. And then buildings that exceed their emissions must pay annual fines. So the performance gap problem, this is what we're trying to solve with the Energy Improvement District. So implementation challenges, so it's complex new technology, the ownership and building owners with lack project management capabilities. Each project is standalone. There's no scaling benefits, and then there's limited workforce experience. Difficult owner decision making. So traditional information only models that exist currently today is fragmented educational models. So it's really relying on the building owner to understand everything that's out there, put all the pieces together, and then create retrofit packages that equal the necessary carbon reductions. It's very difficult for a lot of owners. And then high upfront costs. So upfront costs for retrofits can cost $150 per square foot. As we'll see later, Maya will get into, there's a big economic performance gap and only utility savings of 25 cents a square foot. So big disparity in payback periods. Our payback periods we found could be 600 years in a 100 square foot building. So obviously that's not great. And the incentives for local law 97s is sometimes low, sometimes doesn't cover everything. It's a little confusing for the owners to access and see. So what we're trying to do is the whole point of this is a community energy model that helps solve these issues and push the buildings collectively to achieve decarbonization goals. The first one that we're going to go into is a phased retrofit model. So obviously the major consumption from buildings is from either heating systems, cooling systems. For this, we focus really on the phase retrofit of the heating system. That makes up 70% normally in a multifamily building of their energy use on site. So how we do this? So decarbonization phases, we're going to start, this is our baseline building with our site EUI, so it's energy use intensity. So it's per square foot, kilowatts per BTU per square foot per year. This is the average. So it's a gas boiler, so natural gas. Boiler efficiency is 80%. No envelope work, which is the exterior of the building. Peak load is 101.45. So, but really what's important is natural gas, 40,000 therms, total electricity is 501. So an EUI, we use that specifically because that's how local law 97 issues fines, issues compliance. It's what they use to compare buildings. It's a case that equals everything or keeps it on level playing field. So phase one, tune-up boiler controls air sealing. We're going to go into each one, so I'm just going to summarize it. Phase two, partial electrification, and phase three, full electrification. The idea is that these are not separate phases or separate packages. They are a continuation of each other to try to reach down through to that 21 site EOI or 63% reduction, which will help these building owners achieve their decarbonization goals to avoid fines. So phase one, very important. So this is our low-cost solution. This is something any building owner can do very quickly. It's going and deploy capital very quickly. So it's really focused on boiler efficiency of the existing boiler itself. So there's two ways to really do it. So one is going to be to increase efficiency at combustion, and two is going to be reduce the total runtime of the equipment. So that's going to be through replacing the jack shaft linkages. So think of it as they're manually set. They manually mix the air and the fuel together, and it degrades over time. So if it's 15 years, your efficiency could be 70%, and you have no idea, just because those manual linkages are deteriorating. Replacing that with parallel positioning automatically adjusts the air to fuel ratio, so you get the best combustion, so you don't lose your energy. And then boiler optimization platforms. So there are specific platforms that we looked at. This is all through technical reviews with the actual parties themselves, that are low-cost solutions, and they do boiler optimization. So they might provide an indoor or outdoor temperature reset. So what that means is that the boiler in a hydronic system, the water temperature changes, as does the outdoor air temperature. So the higher the outdoor air temperature, the lower the water temperature. So it ends up being a low temperature solution. The boiler cycle runs for a longer period at lower burn, so it ends up using less fuel. In this phase two, very important, and this is going to be a theme throughout, air sealing. So air sealing, preventing that infiltration, which helps to reduce the heat load, helps to reduce the stress on the heating systems. And a big point of this too is combining with local law 11. We'll get really into local law 11 later with Rajvi's section. But local 11 is required facade inspections and repairs, cycling every 5 years for buildings over 6 stories in New York City. So a lot of the buildings in Community Board 9. And then this phase would be focused on starting with Energy Star scores of D, which is 55 or below. That's really just to get these owners going, get these owners moving. Usually if you're in this realm, and this also covers a vast majority of buildings, it's in the first phase of this was 58% of buildings are D or below. So there's a big area of improvement for this. And the result of this too, you can't really see up in the top. I gotta change this. Is 7% EUI reduction, which is huge. Huge. That is a huge reduction doing a very minimal amount of work, right? How do we go next? Oh, okay. There we go. So that's phase one. We're set up. Phase two, we go and build on phase one into partial electrification. So this is the introduction of heat pumps, right, into that heating system. So your natural gas hydronic boiler, in this sense, right, will have the ability. So what we're going to do is we're going to size the equipment at 50% of the load, right, which is in preparation for phase three, so that the air to water heat pump in a hydronic system can supplement the natural gas boiler, reducing the amount of natural gas used and overall site UI. And then for steam generating buildings, this is an emerging technology. There are some great case studies on it throughout the world in industrial settings. And in New York City, there's some good cases that are happening. They're not live yet. But this is attractive because you don't have to change the distribution system of the steam, which has been historically what you need to do to gain efficiency, is converting it into hydronic. And then building automation systems, and if you have the right ventilation system, an optional HRV, ERV, which is heat recovery, more heat load reduction. The building automation system allows you to tie in your new electrical equipment. You can operate it digitally, you can operate it outside of the site. This is very important when we get into phase four. So this is phase two, right? Size 50% for the heat load for the future, taking over some of the domestic hot water. This is in anticipation of phase three, which we'll get into. And this is also phased along with this local 11. So we're talking about 5 years into phase two. This helps with the capital outlay. And then the last section is full electrification. This is your deep energy retrofit. So this is what usually building owners start with, which is really tough to swallow when you're going through and saying, okay, you have to spend $150 a square foot, so you'd spend $15 million right away to achieve your goals. So instead, what we've done, we've already phased two, so we're building up to this. So now what's happening is, so now you have your third cycle of local 11. You're doing your full scale envelope to reduce the heat load, which is the goal is to reduce the heat load by 50%, so that you can fully turn off your natural gas boiler, use your existing heat pump system that you've already installed in phase two, and either leave the boiler there for supplemental heating in super cold conditions, or decommission it and prep for battery storage areas, which we'll get into. And then this couples in phase 3 with the deployment of a master systems integrator. So what a master systems integrator does is it handshakes with BAS systems, building automation systems, and ties multiple buildings together. So it's an endless amount. It's cloud-based software, so you could tie in 50 buildings if you want to, which is important for our community management model. And then you achieve 63% EUI reduction, which is obviously an incredible reduction. So then phase 4, which is really where the EID comes into play, is the community energy management model and demand response. So now you have your master systems integrator. It's localized to maybe a community board, an area that's looking through this. You have real-time APIs. You ingest all the building automation systems. You can see neighborhood level thermal profiles, neighborhood level energy profiles. You can verify that your deep energy retrofits are actually achieving the projected models, which is a huge thing that we saw in the literature review that does not happen all the time. And then you also are able to collect on demand response. So demand response, it very simply is a load shedding. There's a bunch of different programs, but through the NISO or through Con Edison, as a single building, if you can't drop 100 kW in load, you don't qualify. So as a single building, you're 30,000 square feet, you're never going to qualify for this. But as a collection through your master systems integrator of 10 buildings or more, you can curtail 500 kW, and then you qualify for the demand response. So you can get that revenue back. And that is what we're projecting for $25,000 to $75,000 a year annually in revenue, which is huge, right? That's great. You're reducing your on-site use even more, and you're making money from it, which is not available to building owners in a fragmented sense. And this whole solution is based on resource efficient decarbonization. So that was a phased approach that came out of the Empire Building Challenge. There's a ton of literature on that. There are real case studies that are proving this out as a successful model to decarbonization. And even with large capital outlays and various phases, tons of phases. The reason and the EID governance, like we want to try and target entry points for different types of buildings, just so it can collectively happen as a community and decarbonize as a community. And now we are going to get into the economic assessment.
Thanks. So Joe has talked a bit about why these deep energy retrofits are so challenging, and a big part of that is the financial performance. As he mentioned, we're going to dive a little deeper into that. So HRL 1 and 2 both did spend a fair amount of time looking at the economics of this type of work as well. And there were a couple common themes that came out of both of their work. The first is, yes, deep energy retrofits do come at a very high cost. And moving to electrification is not cost effective because electricity is more expensive than gas right now. The next thing that they found is there are a lot of incentive programs through Con Ed or the city or the state, but the average amount of offset that any one project receives is only about 15% of the project cost. So you have to stack these programs, but it's really hard to navigate that landscape. And the third finding is that it's actually not all about just dollars and cents. There also is a behavioral and psychological blocker to this for many people. People are risk averse. They're resistant to change. And owners also have a tendency to undervalue long-term returns. So future savings that they might receive, people don't really think about those. So we took this and we built on it. Neither group actually put together a comprehensive financial model. They acknowledged that this would be difficult. And so that was what our focus was. And in doing so, we really got a view into what we're calling the economic performance gap of this work. And a lot of our findings echo what the other groups found. The first, yes, this type of work remains very limited by poor economics. And savings in energy or avoiding local law 97 penalties aren't enough to offset the cost of the work to make it worth it. The next is Yes, fuel switching, moving to electrification, actually has negative financial implications in many cases because electricity is over 5 times the price of gas today. And the last is because this is expensive, you can phase the work via the red model that Joe discussed. This improves the economics, but really only modestly. It's still a very cost-intensive undertaking. So as I said, we went ahead and our goal was to build a model that would give us a view into a hypothetical 100,000 square foot apartment building in the city. And right here, you'll see all the costs associated with this work. So that top row is a like-in-kind replacement. So we're assuming that the work would only be completed at the point at which the building owner would need to replace their existing equipment anyway, like at the end of its usable life. So because you're already going to have work that needs to happen there, everything beyond that, you only have to consider like the incremental cost. The owner would have to spend $5 a square foot or $500,000 to just replace their boiler. So you might as well move towards this energy retrofit pathway. And what really emerges here is that as you move into that deep energy retrofit, you'll see, reflecting that reduction in EUI that Joe found. We have a 75% decrease in annual electricity usage here over that baseline, and only about a 10% increase in utility expenses. So again, because of prices today, this owner spent $15 million on this work, and they're saving $25,000 a year. So that's where that 600-year payback period that Joe mentioned comes from. So we pulled all this information together along with other factors like an interest rate that the owner might have on their loan, incorporating local law 97 fine avoidance, which you can take as like a cash inflow, increases in utility rates over time to develop a more comprehensive, nuanced view of the cost effectiveness of this work, which we are representing as the net present value of each investment here. And this is, you can take this as a measure of return on investment in today's dollars over a particular time horizon. In this case, we looked at 20 years, which we took as that was our assumption for the equipment's natural life, when you replace pieces of it again. So a positive NPV indicates you had a positive return, negative, you lost money in today's dollars, and 0 is you broke even. As you can see here, after phase one, you have a modest positive return, but the minute you get to that more cost-intensive work, you're losing quite a bit of money, all the way up to over $2.5 million in the case of that, doing that full deep energy retrofit all at one point. So, okay, we wanted to take this and say, how can we close this gap? How can we make the numbers look a little better? And we focused here on 3 variables. The first, increasing local law 97 fines. If you raise the cost of doing nothing, it's going to look better economically to do something. The second is that landscape of incentive programs that HRL 1 and 2 pulled together. So these can be used to reduce the upfront project cost, the whole cost of the work. And then the third is access to lower interest capital, getting loans at lower interest rates. And we conducted a sensitivity analysis, modifying each of these variables in different combinations in order to look at the impact on that net present value. So starting with the local law 97 penalties. Today, the penalty for an owner is $268 per ton of CO2 that's over their annual emissions limit. And what we found is, so phase 1, already cost effective, no need to raise the fines. Phase 2 and 3 have to increase to 12 to 20 times the current rate. I think we all know how much influence the real estate community has in New York. That's never going to happen. But it also emphasizes just how insufficient the fines are today, which is unfortunate, but it's the reality. So we then focused on the interest rate and any possible incentive program reductions. And in doing this assessment on NPV, two kind of really unexpected trends came out that surprised us. And you'll see this reflected in the numbers, but just to outline them here. So generally speaking, a lower discount rate is going to increase your net present value, because what you're basically saying with that is that a dollar in the future is going to retain more of its value of the dollar today. So flipping that, like if you have a 4% discount rate, which I should have mentioned is the assumption that we used earlier, that says that a dollar today is going to be $1.04 in the future. And the other thing that you would expect to increase net present value is having greater reductions in upfront costs. So a higher incentive should also improve the economics of your investment. However, two trends emerge from here. So the first is when you have predominantly negative cash flows, which is the case in these retrofits, a higher discount rate actually helps increase your NPV because you're minimizing the impact of those future losses. So in today's dollars, those big negative outflows in 15 years are going to be smaller. And the next trend that we found is that when your discount rate is higher than your interest rate, you actually have a higher NPV with more money that you take out, which is very hard to wrap your head around. But essentially, when debt is cheap, borrowing money creates value for the owner. This is called positive leverage. You can think about it as future repayment costs are going to be less in today's dollars. So you actually end up spending less than the original value that you took out. It's reflective of the time value of money here. And oops, I should say that's what the numbers show. That's not necessarily what an owner should or would do. Like that's the math. I think it's safe to assume most people would not say, oh, I'm going to take out $15 million instead of $10 million because this one measure makes it look that way. So looking at that combination of interest rate adjustments and incentive programs, we modeled the NPV at interest rates of 1 through 7%, one being there are some programs available primarily to affordable housing buildings that can get down to 1% interest. And then we looked at incentives from 0 to 60%. And we found that with different permutations of these, you actually can make the investment make sense. And the biggest impact that you have is lowering the interest rate. As you can see here at 1%, every phase of work is positive with no incentives. But again, some of these programs only available to affordable housing buildings. So how can the EID help? And Monica will go more into this, but there are a couple areas based on what we found where the community approach can make a big difference. The first, consolidating that information on all of the capital programs, having funding advisors to help owners maximize the amount of incentives they received. The next, strategic support with financing. So connecting owners directly to banks. We'll have trained loan packagers that can help an owner find the best package for them, try to secure the lowest interest rates possible. The third is the benefits that you get from completing this type of work at scale. You know, you're a group purchasing equipment, you can get bulk discounts. Rather than each owner individually working with an engineer to design a very custom solution, which is expensive, the EID will have standardized packages depending on building typology. The last, completing multiple installs in the same geographic location. You get the contractors, all the teams out there at once. You're going to reduce the costs of getting somebody to your job site. And then also sharing knowledge over time helps this work get done faster because you're improving that learning curve. And lastly, advocating at a policy level. So expand eligibility to these programs to market rate buildings, and also work with regulators to address this electricity to gas price disparity, which we have seen is a big impact. And now I will pass things over to Rajvi to talk about something that can kind of put a wrench into all of the financial modeling.
Thanks,
Rajvi, do I need to control this? Do I need to control the screen? So
yes, I
okay.
think so. Thank you.
Yeah.
So after looking at the economic assessment, we also wanted to understand the practical implementation barrier that make deep retrofits difficult in New York City multifamily buildings, especially with exterior wall insulation. So to begin this analysis, here are some of the main findings from previous teams, starting with research that shows exterior envelope upgrades offer the greatest energy saving potential in multifamily buildings. It also showed that continuous exterior insulation works really well because it improves air tightness and reduces thermal bridging. But at the same time, Harlem buildings have a lot of retrofit challenges, especially pre-war buildings with fire escapes, balconies, and complicated facades. And another important point was that advanced retrofit systems like panelized facade have strong future potential, but right now they are still very expensive and difficult to scale. So, after reviewing these findings, the next question became, why is wall insulation so important for deep retrofit performance? Next, please. Thank you. One major finding from previous studies is that the deep retrofit performance depends heavily on wall insulation improvements. So things like electrification and air sealing definitely will help, but if the building envelope is weak, heating demand still stays high. So that's why envelope performance becomes really important for long-term energy reduction. And while exterior insulation is technically effective, the problem is that implementation becomes really difficult, like when projects are done one building at a time. And before we discuss the implementation barrier, yeah, here are some of the main exterior insulation retrofit approaches, which includes continuous exterior insulation, which improves thermal and performance and air tightness, but facade access can become difficult. Then if is an overcladding system that can help reducing retrofit costs, but sometimes there are code or facade limitations. Next is penalized facade system that are interesting because they allow faster installation, especially for occupied buildings, but the upfront costs are still high. And then the retrofit prefabricated system that can support near passive house performance, but they still have limited adoption at a larger scale. So basically, every system has the advantages, but also different implementation challenges. And that leads directly to next question, what is actually driving this retrofit costs? And to understand how this system perform in practice, let's look at the existing retrofit precedents projects in New York City, including Riceboro and Passive House retrofit case studies. So these projects demonstrated that deep envelope retrofits are technically achievable in existing multifamily buildings. The case study consistently showed that significant wall insulation is necessary for major heating demand reduction, and that continuous exterior insulation improves air tightness and reduce thermal bridging. But at the same time, they also showed that successful project required strong coordination, careful rehabilitation planning, and extensive construction management. So even in successful projects, scaffolding, facade access, scaling issues, construction logistics remain major cost barriers. So the issue is really not improving or proving the technology that works anymore, but the bigger challenge is now scaling these retrofits across existing multifamily buildings. Next, please. Yes. So, and another cost barrier is actually facade access. Again, not the insulation technology. So the real challenge comes from the construction process required to install them. And major cost drivers, including scaffolding, sidewalks, mobilization, then tenant protection, facade coordination, and construction sequencing. So these costs occur upfront before energy savings are realized, which makes exterior insulation economically difficult for many building owners. So in many cases, the issue is less about whether the technology works and more about whether building can realistically manage the construction complexity and upfront implementation. So once facade access becomes the main issue, it starts changing how we think about retrofit implementation, which is next slide. So from building retrofits to district coordination, this led us one of the major conclusion of our section. Deep retrofits become very difficult when they are approached one building at a time. Owner by owner implementation does not scale efficiently because every project repeats the same excess costs, mobilization efforts, and coordination challenges independently. But if buildings are coordinated at the district level, there are opportunities to reduce repeated costs through shared scaffold access, coordinated phasing, and shared procurement strategies. And we also identified local law 11 facade inspection cycle as an important opportunity, as Joe mentioned earlier, for coordinating retrofit timing with required facade work. So ultimately, we found that primary challenge is not technological. The bigger challenge is organizational and economic coordination. And finally, after looking at the coordination and implementation challenges, another important factor in the retrofit feasibility is how building geometry, next slide, affects the retrofit feasibility. So even with similar floor areas that can be shown in the picture, can have very different retrofit conditions depending on facade exposure and building configuration. For example, mid-block buildings usually have limited exposed facade area, while corner buildings or light coat buildings are much more complicated because of the scaffold access and sequencing. Another important issue is that insulation costs are usually quoted per square foot of wall area, while overall project economics are often evaluated per square foot of floor area. So because of that, we introduced this wall to floor ratio factor to better related exposed facade area to total building of floor area. And overall, the result in the table showed that geometry also plays a major role in retrofit feasibility, implementation difficulty, and overall project costs. So yeah, overall this findings show that challenge is no longer just technical, it also organizational and implementation based. So by saying that, I'll now pass it over to Monica.
So now that we have discussed the challenges of building decarbonizations and some of the solutions, we want to show you what is happening right now. What are the building owners getting, that support that they're getting right now? So there are some programs such as the New York City Accelerator and the NYSERDA Energy Hubs, that they're providing some technical guidance, some connections to fundings, some referrals to technical resources. However, all this information is very scattered. It's coming from different sources. They have to go to different organizations, different websites. And this information is given to one building at a time. So it's not given to a group of buildings. So they're waiting for the building owner to come to them to really get this information. So this is not what the building owners need. They need a different support. They need someone that they can take them from that planning stage to implementation. So what is that additional support that building owners need? So the one possible solution could be the community scale approach, where buildings, like a group of buildings, come together so they can really share learning. They can really support each other and just create that opportunities to possibly reduce lower project costs, have a stronger coordination. They need that dedicated project manager with them so they can take them from every stage of the process. And they also need that long-term technical, financial, and community coordination. So they need someone to take them to navigate fundings, to show them opportunities such as demand response programs, and just having that ongoing support from all the stages. So what are we proposing? So we are proposing an energy improvement district to help overcome technical, financial, and implementation barriers to building decarbonization. So we are focusing on Community Board 9. This covers Morningside Heights, Manhattanville, and Hamilton Heights from 110 to 155th Street. And the goal here is to create a framework that could potentially be expanded to other neighborhoods in New York City. So I want to show you the organizational structure, the possible organizational structure for the EAT. So we see the EAT in the middle. So the EAT is the facilitator, the one that is gonna help connect the building owners with the service providers, with the local organizations, with the financial institutions. But we also want the EAT to work closely with the Community Board 9. So this will be the lead institution, that anchor institution that is gonna show us the way that they already are working. So we know that the community board is already working with local stakeholders and they have an existing neighborhood structure. So this could help us coordinate discussions and identify priorities within the community. To understand how an organization like this could work, we review the bid model. So these we know that are bids that show how property owners can come together and work to improve something in the community. So it could be anything. In this case, we could use it to work towards building decarbonizations and energy upgrades. And we also review the community benefit agreements. So this could help us to ensure that the benefits remain measurable and they are accountable to the community that we're working with. Now, what could be the potential funding sources for the EAT? So first, city appropriations through the Community Board 9 could be requested through that budget that they request every year, so to support neighborhood decarbonization efforts. Another option is to leverage grants, rebates, and incentives. And also, we want to give the opportunity, they have the opportunity for demand response revenue. So one potential partnership that we reviewed is the 125th Street bid. This is a bid that is already established. So it could be easier, let's say, to work with them to implement this type of programs. And also grid participation and renewable energy revenue is another source. How funding could be used? So this could be, the capital funding could be used for equipment, for system upgrades, for energy audits, for demand response equipment. The expense funding, those ongoing needs could be used for technical support, for energy engineers or that project manager that we talked before, and for software and monitoring. Now, we want to just mention what we did. So the stakeholder engagement that we did and the outreach. So we interviewed different stakeholders from community organizations and technical experts. We conducted outreach to Community Board 9 and 125th bid to explore potential partnerships. And we also attended some local events to understand Harlem's priorities and sustainability efforts. So some of the findings, let's say, is that they gave us a lot of feedback about our proposed EAT. They tell us honestly, like if they think that this could work or not. One of the maybe challenges that we had with them was few of them. They were very committed during our meetings, but maybe after when we were sending follow-ups, we got some emails unanswered. But mostly it was a successful engagement. When we tried to do the outreach with Community Board 9 and 125th bid, this was more challenging. It was hard for us to find that right contact, that right network to really have that person that can work with us so we can present this idea to them. But so overall it was fine, but I just want to mention something that we got from them. some of them, they mentioned that we need to work when we're trying to get participation from the building owners, we need to work through trusted organizations. So, and this can help me introduce a concept that we reviewed during our literature review, that is diffusion theory. Which this explains that people do not adopt new ideas just because they are getting a benefit, in this case, like a technical benefit. They are also looking at other factors, that adoption is also influenced by trust, by communication, how people perceive those benefits that they are getting, and how information is spread through those trusted networks that they really trust, let's say. Yeah, I think that's it. But overall, I think this was a learning experience for us. I think building partnerships takes time, and that it's important to find that right connection, that right network for this to really work. We just want to mention briefly what methodology we use. So we did review of literature and case studies. We did community engagement, as I mentioned before. And for our quantitative analysis, we use Excel-based calculators. For the next step, so we're thinking about the next group that is coming, HRL5. So there are a couple of suggestions that we have. So the first one is to work with Community Board 9 to develop energy improvement goals through existing committees. A second one could be to host sessions with building owners and tenants to better understand their needs and get feedback. And the last one could be to invite government and public stakeholders to join as committee members. Thank you so much.
So, hi everyone, good morning. And we are presenting on the enlistment of remote sensing tools for deployment of renewable energy infrastructure, led by Professor Kyle McDonald, that's Sullivan, Pravil, and me. And our work is mainly driven by data-driven planning for growing, skyrocketing in energy demand. What we are facing here is an energy tsunami, where by 2030, it is projected that global data centers are going to double, and the EV charging is going to quadruple. And to meet this, we must identify the optimal renewable energy sites with unprecedented speed. That current planning faces a perfect storm with rising complexity and the lack of real-time data and the massive computational load that requires to optimize the grid resilience. So we began by reviewing 20 papers at the beginning of last semester across multiple technologies to assess how remote sensing is currently applied and where the methodology gaps remain. And we identified 3 pillars. The first one would be the global remote sensing reviews, and then the specific data applications, then the regional hybrid site case studies. So for this, we choose Google Earth Engine as our primary tool because it provides a unified cloud-based platform for multiple sources of data integration. More crucial to us is the GE allows us to perform cloud computing on massive data sets by passing all these local hardware limits to extract long-term trends. So our GEE flow is pretty much straightforward. We gather multi-source data from land cover to nighttime light and assess indicators such as digital elevation models and surface temperature, execute on the cloud scale formulas, and then finally run the with suitability analysis to visualize suitable sites. So our main focus area is New York State. Why? Because it's legally committed to a zero emission electricity system by 2040, including upgrading to 10 gigawatt solar, then the 6 gigawatt of energy storage, and 9 gigawatt of offshore wind by 2035. And I'm now going to pass it on to Pravil to start the focus on the area focus in New York State with solar energy.
Hi, so I worked on the solar and the wind analysis, and both of them use a 5-factor scoring framework. So to start with the solar, this is the first layer, and this is the annual solar resource across New York State. We can see that Long Island and the city itself, New York City, gets the most sun on the scale. The darker it is, the less solar irradiance it is, and the lighter blue into the green is the higher radiation that the surface receives. We see that the Finger Lakes and the southern tier is pretty solid, but then that darkest spot is the Adirondack Mountains, and that loses out to solar radiance from cloud cover for the lakes and everything. Now, in solar, sunlight is the most important factor, right? So for each technology, we have a analytical hierarchy process. So it's an AHP, and we weight each of the layers. So for this specific one, it's almost 50%. It's 49.1% in our layer. Secondly, we have land cover. The bright green overlay on the map is what we have flagged as suitable for utility scale solar. That's open developed land, barren ground, pasture, and cropland, right? We can see the trends are that there is the open suitable land clusters in Western New York. That's the farming corridor. I've excluded the forests and the forest zones because clearing trees and deforestation for utility scale solar kind of undermines the entire climate benefit. The next layer is the terrain slope, and this matters a lot for solar. Anything steeper than 5 degrees gets pretty expensive in construction, and it also can actually start to cause a shadow on the panel and decrease its efficiency. So the main green color that you see is what's flat enough. The light yellows are the peaks and anything that goes steeper. Again, you can see the 2 mountain ranges are the main clusters that pretty much get canceled out, the Catskills and the Adirondacks on the northeast side. This is the second most important factor. We've weighted this at 25.4% in the AHP. Next, we have proximity to existing solar infrastructure. The red dots are the existing solar farms, and the orange halos around them are 25-kilometer radius around it, where new projects can benefit from existing grid connections. The trends are that you just see clustering along the I-90 corridor and the southern regions of New York State, right? This is a small weight on the scale, but building near the infrastructure can, it cuts costs, and also permitting for construction has also been established. Moving on to the last layer, it's population density. Population matters because, well, solar needs to be near where the electricity demand is and where it's actually used, but not so close that it competes for housing and land space, etc., especially on a utility farm scale, right? Again, the population clusters are on the I-90 corridor and New York City itself. That's the dominating regions. This is the lowest weighted factor because it's it cuts both ways, right? Too close to people is bad, but also too far from people is bad as well. Now, when we put all of these factors together with their weights, this is the final solar siting suitability map. Few things stand out. First, the lower Hudson Valley and Long Island actually score the highest, right? They hit all the 5 factors at once. There's a strong agricultural corridor on the west that can also be used for solar farms. And the Catskills and the Adirondack mountain ranges are pretty much, canceled out because of the slope and stuff for solar. Now, The best validation for this map, this model, is that several of New York's largest solar projects, including one called Cider Solar, it's a 320 megawatt farm, they fall right into these high suitable zones from this map, right? So it just says that the model is accurately identifying regions that our real developers have been using. So moving on to onshore wind, the first layer is wind speed, right? Wind speed is the most important one at 100 meters. This is the typical turbine hub height for a wind turbine. This comes straight from Global Wind Atlas, which is the gold standard for any wind data that you need. The strongest wind that we see comes from the Tug Hill Plateau on the east of the Lake Ontario and along the shorelines, right? Now, it also is worth mentioning that the Adirondack Peaks on the northeast also have extremely high wind, right? It's weighted at 35% in our AHP. Now, when you get the data from these data sets, you have to normalize it because it comes in like U vector and V vector. So you have to normalize it in order to get usable data, right? This is what that normalized scale looks like. The green areas, you see them clustered in the two mountain ranges. They have genuinely great wind, right? But most of New York actually falls below the threshold. That's why there's so much red for commercial wind, right? This is reality, right? New York actually ranks 15th nationally for installed wind capacity. It just means that they have excellent pocket sites, but it's not, a wholesome resource. So next is the land cover suitability, same idea as the solar. Red is excluded, yellow is forest. Now the yellow is possible, but it gets expensive for wind. And green is fully suitable, right? So that's cropland, grassland, shrubland, etc. Again, the green corridor runs through Western New York's farms and the Mohawk Valley as well. It's not a coincidence because most of New York's existing wind farm is already on the Tug Hill Ridge. It sits in these green zones, right? This is weighted at 20% in the wind scale. Next layer is the setback distance from built areas. Wind turbines need distance from buildings and the built area because of noise and shadowing. Under 500 meters is less than 500 meters away is a hard no. 500 to 1500 is, a marginal buffer zone. And then you're all clear from over 1500 meters, right? Moving on to the environmental and ecological constraints. This combines protected areas, surface water, and forest cover. Now, the Adirondack Park and the Catskill Preserve are two protected areas, so these are hard exclusions on this layer. This is a great thing to note because, as we remember, in the wind layer, those two were actually extremely high, right, on the factor. This layer cancels them out from the entire model because they're legally undevelopable. So this just goes to show why our multi-criteria approach is so useful, because a single criteria would have just said, hey, those are two, gold mines for wind. So the final wind map, we see the strongest corridors cluster in Western New York's farmland, the Tug Hill Plateau, a little bit south of it, and the Mohawk Valley. All these are close to grid infrastructure, it's away from population, and it has viable wind. The strongest validation for this map is that, again, every existing utility scale wind farm is already in these green areas, right? There's Maple Ridge, Sheldon, Wethersfield, all these existing wind farms. So the model accurately identifies the same locations that developers have already been using and they have already chosen, which gives us high confidence that it'll be useful for siting for future projects. So now I'll hand it off to Lee to go through offshore wind and biomass.
I'm gonna try to step over like that. Okay. All right, so let's come back a little bit and shift forward to the offshore wind. And here we narrow down our focus from NYSERDA's Master Plan 2.0, the deep water area at the left side, to specifically the shallow water below 60 meter at the red box, the New York Bight area. So while all turbines, the top one over here, are typically 6 megawatt at the hub height of the 100 meter. We have included the new 15 megawatt, 150 meter standard hub height for standard used in major US and European projects here today. Using a 30-year of the hourly data sets, we identify a wind speed sweet spot. You see where the cursor is pointing at, between 9 and 10 meter per second range. Translating into the US metrics is about 20 miles per hour, and you can imagine how that goes like. And at this range, the 15 megawatt turbine net power, after calculating the wind speed, then the wind power density, then the gross power, incorporating wet loss to the net power onshore, can increase by 240% over the of the 15 megawatt turbine over the 6 megawatt model, demonstrating how the larger sweep area of the 15 megawatt turbine can, at the same location, can exponentially boost its energy output with its sweep area. So the next one will be the sea floor depth. That is pretty much critical for constraint for the our scenario, that the fixed bottom turbines are generally limited to 60 meter or less, as shown in the dark green area over here. And however, the New York State offshore wind industry is actually increasing, eyeing on the yellow-green area, slightly below it, with depths ranging from 60 to 200 meters. And this distinction is vital only because that the depths beyond 60 meter require floating turbine technology, which brings significant higher cost for installation and infrastructure. In terms of the site to shore distance, we are eyeing at the key operational factor that the 0 to 27 kilometer at this part over here allows for daily shore-based commute. What does that mean? Which means then when the crew member or the workers have to ship up the tools to install turbine and do some other maintenance, they can only do that on a daily basis when it falls into this range. While the anything beyond that, up until 80 kilometers, is usually require like overnight to month long of the offshore wind stay for the crews. And we have defined the 800 kilometer port. And the port is this one over here, which is the Brooklyn Navy Yard terminal, that the port radius as our efficiency limit, because beyond this point, volatile sea conditions and extended travel times makes the maintenance mission physically and economically demanding, particularly on a single day maintenance. Similar to how we generally avoid going out to the sea during kind of like a heavy rain or windy day, only because the offshore operations are highly constrained with rough weather conditions and also ocean safety risk. So now we're going to move forward to look into the other ones, which is the slope constraint for the seabed. Anything below 5 degrees is actually better in comparison to steeper terrain, because that would require to compromise the stability of the turbine foundation and also cable burial equipment. That the steeper slope usually require costly seabed leveling, and then that increase the environmental disturbance as well. Additionally, our suitability analysis strictly exclude marine protection area, which is the pink part, the purple part over here. And then to ensure that the Lautenberg coral protection areas is included in our analysis, that we avoid conflicts with the sensitive habitats and also minimize the ecological impact. Here, we see a lot of yellow color around here, which is the nighttime like that we use to visualize the high density shipping and commercial fishing activities at the Northeast region, particularly important because the offshore wind operations usually try to avoid these areas to reduce the navigational conflicts and improve maritime safety. And the data also helps us to explain why U.S. projects these days are using uniform one by one nautical mile turbine spacing to maintain predictable transit corridors for commercial vessels, unlike the tidal layouts that often used in European regions. So for our final layer, we prioritize access to the 345 to 500 kilo voltage of the onshore connection points, because these connection points are the backbone to and the only existing infrastructure that capable to absorb the massive 50 megawatt turbine output without causing significant energy loss or grid bottlenecks. So let's come to the suitability layer. We weight the wind speed at 50% because this is a primary driver and catalyze to balance out as the revenue driver, and against the water depth of 20% and other factors at 30%, which can be the operational and grid constraint that also indicate construction costs. This weighting prioritizes high yield zones where 50 megawatts of the the sweep area can economically offset the logistical complexity of deep water infrastructure and maritime protection. So at a suitability threshold, our model identifies optimal zones that align closely with the current New York bight area, which is someplace over here, as you can see. And now, with that being said, we are going to move on to biomass. And for a biomass layer, we focus on 3 primary crops in New York State, which is corn, soybean, and also the winter wheat. And we use 9 years of the data, such as the enhanced vegetation indices and shortwave radiation data, to measure the solar energy that being absorbed over the 168 days of a growing period. And by applying the light use efficiency and also the harvest indices, we separate the eatable grains with the energy from the energy-rich dry residue. That can help to project the actual energy potential in the New York State by itself. And at the green area over here, these are the agriculture farmlands that shows the actual energy potential for biomass energy production. For biomass suitability, we also prioritize the slope that's less than 4 degrees, only because steeper terrain usually increase the risk of the soil erosion and also make the heavy machineries to harvest and transport the bulky residue from both unsafe and economically insufficient or inefficient, actually. And then we also use the Retire Black River facility as our logistically benchmark as the only large-scale dedicated biomass plant in New York, positioned near the major culture hub here, the blue point over there. It serves as the ideal case study for us to prove that 50-mile transport distance radius is actually it's a economic tipping point for moving bulky crop residue to a high capacity power node. So let's move on to the grid proximity. Biomass plants usually interconnect with the medium voltage of the transmission lines. And our results show that high suitability zones are concentrated where the existing grids overlap with the 50-mile collection radius. The green part is the most suitable one, allowing projects to minimize capital-intensive transmission loads. Finally, last but not least, we apply the world database on protection areas as a binary mass to strictly exclude state parks, sensitive habitats, national parks, to ensure our suitability layer respect legal conservation mandates and also biodiversity goals, keeping the biomass production entirely outside of the restricted territories. So, for the suitability test, we weigh crop yield 50% as our primary indicator, only because that would highlight the net productivity, directly determine the volume of residue for energy potential. Then the plant proximity and grid access 20% each, representing the essential infrastructure needed to ensure the high yield biomass that can be cost efficiently transported and successfully interconnected to New York State's power grid. The last one is the last two, 10% on the slope, only because we recognize that it's essential for preventing soil erosions and ensuring the harvesting safety, but it also acts like a localized topography constraint rather than the primary driver for regional energy potential. Finally, the wall protection area, legal protections that serve as our definitive environmental filter to ensure that all development remains on viable and non-restricted farmland. So what the final map is telling us is that once we look into all these layers, stack them up together, the optimal biomass zones primarily concentrate in the finger-like areas, right here, and also here, due to the existence of the plant site. Then I am going to now move on to Sullivan, that we can start talking about hydropower.
Okay. So hydropower has been an important source of electricity in New York State since the late 1800s. In 2024, New York was the third largest hydropower producer in the US, with hydro providing over 20% of the state's electricity generation. While large dams like the Niagara Power Plant account for the majority of hydropower currently produced, there are growing opportunities for smaller run-of-river hydro plants which use existing river flow rather than storage reservoirs to generate power and are considered to be more environmentally friendly. Okay. In order to determine suitable locations for additional hydropower in New York State, many factors had to be considered. A study by Meryl Korkmaz out of Münster University in Turkey provided much of the framework for our evaluation. So first we looked at river order, a classification determined by the long-term average discharge rate of each river. And we have river orders of 3, 4, 5, 6, and 7, all of which are suitable for hydropower. Next is drainage density, which is calculated by dividing the total stream length by the basin area. Then we have average annual rainfall, the greater preference for rainier areas, although New York is pretty rainy on average. After that, we incorporate slope and elevation, prioritizing slopes less than 6 degrees and lower elevations for greater flow accumulation and easier access for construction. After that, we assess geology, looking for areas with low permeability to keep water from seeping into the ground and also to provide a structurally sound space for equipment. Similarly, the land use land cover, prioritizes the bare surface areas and excludes built up areas. Oh, sorry. Okay, so then each of these subclasses are ranked from 1 to 9, with 9 being the most conducive to hydropower siting. The criteria layers are then weighted according to the analytical hierarchy process, with river order and drainage density both weighted the highest at 25% each. From there, we get our hydropower suitability map. And then in order to assess the accuracy of the map, we added another layer with locations of existing hydropower plants that you can see in kind of the black circles there. And those were assessed in a study commissioned by NYSERDA in 2016 to find hydro eligible for capacity upgrades. The existing sites were sampled against the suitability map and were found to have a mean alignment score of 69%. The last renewable energy technology we looked at is energy storage. While there's many promising types of energy storage for this project scope, we chose to focus on battery energy storage specifically. New York State has a goal of installing 6 gigawatts of battery energy storage by 2030, and currently has 528 megawatts installed with another 1 gigawatt in the pipeline, meaning another 4.5 gigawatts must be developed in order to meet the goal. To understand what locations were best suited for battery installations, we looked to the 2025 Fire Code of New York State, which was just released like in January, which specifies batteries must be released or must be placed in at least 10 feet away from buildings, vegetation, roads, lot lines, and hazardous materials. So the map layers that we used for energy storage include land cover, protected areas, the digital elevation model, global settlement characteristics, and substation data from National Grid and transmission lines. The first step was to mask out all of the unsuitable areas, including water, forest, crops, protected areas, and slopes greater than 5 degrees. Then we also created a 10-meter buffer zone around buildings and high vegetation. And we used 10 meters instead of 10 feet due to the minimum resolution of the data set. Lastly, we targeted a 5-kilometer proximity radius to substations and transmission lines. The proximity radius was weighted the highest in determining the most suitable battery energy storage locations, as connecting to existing utilities can be one of the biggest cost factors in creating new systems. And finally, we compared our suitability map to NYSERDA's data set of installed ESS over 5 megawatts and found a mean alignment score of 56%. Because the Energy Code provides general guidelines, future work on this mapping tool could include adding municipality-specific zoning requirements. While roads and lot lines are included in the setback requirements, loading such large data sets at the state level was not feasible at this moment in time, but could provide more accurate estimation at the local level. So wrapping everything up, our final suitability analysis. Once the suitability scores for each of the 6 renewable energy types were ready, they were normalized to a 0 to 1 scale and exported as an image asset in Google Earth Engine. Then each suitability image was loaded back into the script together and mathematically compared. For each pixel within the state boundary, the highest scoring renewable energy type was determined, assigned a color, and added to the map. The result is the map on the right, which shows where each technology has the highest suitability in the state compared to the other 5 technologies. So this map represents the culmination of 2 semesters worth of research and skill building for our team, as all of us were new to using Google Earth Engine at the beginning of this Capstone project. This map also represents a jumping off point for continued research into renewable energy suitability in New York State. Future work could include calculating generation capacity for each renewable energy shown, as well as economic analysis and emissions reductions estimates. Ideally, the map could become a tool for various stakeholders such as communities, local governments, developers, and landowners to better understand what types of renewable energy are best to their location and needs. Ready?
All right. Hi, everybody. My name is Olivia. I'm joined by my teammates Dante and Judy. And today we're going to talk to you about affordable housing and climate risk. Ooh. Ooh. Okay. So we'll start by giving you some background research we found and just introduce the problem and motivation of what we're trying to add and what we're trying to look at. Then we'll dig into our objectives and methodology, which was in 2 phases. The first is data assembly, the second is data visualization. And then we'll dig into some initial results that we polled. Each of us will dive into a specific climate risk. So we'll look at urban heat, coastal flooding, and air pollution. We'll present our overall findings, and then Judy will end the presentation with the challenges we incurred, future research, and just our overall conclusion. Okay, so as an introduction, again, in the US, housing is a critical element of any infrastructure investment strategy. Safe and affordable housing provides security and stability for residents to thrive. Affordable housing in high opportunity neighborhoods with good schools, good jobs, and healthy environments supports vibrant communities and connects people to employment and helps families climb the economic ladder. However, the United States is currently facing an unprecedented housing affordability crisis. This impacts community vitality and households' abilities to surmount challenges ahead. At the same time, communities are also facing increased climate risks. Up to 1/3 of the US housing stock is at environmental risk. Natural disasters worsen housing scarcity and displacement. Due to this projected increase in the duration and intensity of extreme weather events, such as fires, heat waves, and flooding, the US affordable housing infrastructure faces catastrophic losses due to its availability and habitability. Okay. So climate risks are increasing, and unequal recoveries push vulnerable populations to the most dangerous housing outcomes. Meaning when natural disasters occur, recovery money tends to flow to already advantaged neighborhoods, leading to a disproportionate loss of affordable housing. And this ensuing displacement leads to higher rent burdens, overcrowding, and mobility into inadequate housing. These can inflict health issues and reduce access to supportive services and communities. Therefore, building for resilient futures requires systematic investment in affordable housing. And there's a need currently in this space for data-driven, equitable solutions. And we need to bridge building level insights, demographic data, as well as climate risk modeling. So with that in mind, that brings us to our project objective. So in this project, we aim to develop visualizations and analyses of heat, flooding, and air pollution risks to federally assisted tenants and their housing units. So just to break out like these 2 tasks that we went through, first, we aim to integrate and visualize multiple data sets. That means compiling data from multiple sources and merging them into a single data source. And this data includes climate risk data, land use data, and assisted housing and demographic data. Next, we attempted to use those data sets, visualize them in ArcGIS tools, and develop integrated climate housing hazard metrics. So for each risk, we'll present an overall hazard risk score. This kind of the outcome of this is to provide a multi-scalar resiliency model, which can be used for policy strategy or just be an interactive tool from which we will offer recommendations based on our analyses. Okay, just a bit on our methodology and what we focused on. The analysis of federally assisted buildings in this study was conducted at the building address level. And we did this because this is the smallest available geographic unit of analysis. So we have census data, essentially. And the main three types of federal assisted housing we are looking at is project-based Section 8, public housing, which is receives funding from the U.S. Department of Housing and Urban Development, and low-income housing tax credits, which awards tax credits to housing developers in exchange for agreeing to reserve a certain amount of units as rent restricted for lower-income households. And
Thank you, Olivia. Now I'm going to go into the methodology that outlines the workflow for our project. So to begin, we started by defining our research problem and conducting a literature review on the affordable housing, environmental justice, and climate vulnerability indexes. Then we established our research objectives and formulated our hypotheses for each of our 3 climate risk areas of interest. Following that, we assembled multiple different data sets, including demographic data sets, climate risk, land use details, and wanted to merge all of these data sets to integrate within ArcGIS to develop an interactive mapping tool. Finally, we conducted hazard analyses as well as picked our metropolitan comparisons we wanted to focus on, as well as developed the custom hazard risk scores for the 3 climate risks we chose. Just moving into understanding why we wanted to do this formulation of our database in ArcGIS. We wanted to create an interactive tool that could be used for community engagement and continued policy discussion. And our intended users for this interactive mapping tool is community organizations, affordable housing stakeholders, as well as local government officials who are seeking help with integrating strategies for policy and resiliency strategies. All right, now going into the scope of our project. Our project detailed over 55,000 individual properties across the US, and that equates to 4.7 million housing units. Across the 4 metropolitan cities that we focused on, that ended up being 3,316 individual properties. And after dividing up by program type, we saw that low-income housing tax credit made up the majority program type of the 3, followed by Section 8 and public housing. So now moving into the 4 city housing base that we developed. So we chose New York City, Los Angeles, Miami, and Phoenix as the study cases. New York City made up the largest group of federally assisted housing with over 350,000 units. And Phoenix, Miami, and Los Angeles were chosen due to their unique different exposures to heat, flooding, and pollution variables, respectively. All right. Now this slide introduces the Federal Emergency Management Agency's National Risk Index State Percentile. And we wanted to showcase this as it was used as a broader comparison benchmark against the custom vulnerability index scores that we ended up making for each of our climate risks. Unlike our specific vulnerability scores, this variable captures vulnerability across 18 different natural hazards, and the score is ranked across census tracts on a percentile scale of 0 to 100. So higher value indicates greater overall vulnerability. And we wanted to include this variable because it provides a nationally standardized reference point to look to. While our custom scores focus specifically on affordable housing units, this scale focuses on census tracts as a whole. So what we could see here is LA ranked the highest while NYC ranked the lowest using this scale. And now going into our data set selection, we focused primarily on 3 different data sets. The first being the National Housing Preservation Database. And we primarily used this data set because it gave us building level demographic information for affordable housing units, specifically on subsidy programs, target tenant types, as well as occupancy and building age. Secondly, we looked at FEMA's National Risk Index. This allowed us to evaluate climate-specific related hazards, specifically for urban heat and flooding. And lastly, we looked at the Environmental Protection Agency's EJ score dataset, and this gave us good insight onto air pollution exposure. All right, so now we are going to move into the first climate hazard risk, which is urban heat vulnerability. So these were the guiding questions that formulated the analyses that we ended up doing. So we examined whether higher concentrations of low-income households correspond with greater heat vulnerability. We looked at whether older housing units faced disproportionate levels of increased heat risk, as well as we looked into different tenant populations, such as elderly or disabled residents who may be more vulnerable during extreme heat events. And going into the urban heat variable selection, this slide explains why we chose these 4 variables. The first variable, and maybe the most important one that we decided, was the heat wave risk and vulnerability index. So this captures overall heat wave vulnerability, and it also combines exposure, sensitivity, and adaptive capabilities. Then we looked at the pre-1960 percentage variable. This measures concentrations of older housing stock, which are more likely to lack in efficient insulation and cooling systems. And we also looked at low income percentage. This captures like socioeconomic vulnerability and reduced ability to adapt in scenarios of extreme heat. And lastly, although this variable ended up not being included in the formulation of the urban heat risk score, we wanted to look at target tenant type as a comparison because, again, elderly and disabled populations may face increased physical vulnerability in cases of extreme heat. All right, so now as a way of showing off some of the features that our interactive ArcGIS map has, I'm going to go into some of the maps developed out of the data sets that we created. So first, this map showcases a spatial distribution of heat wave vulnerability near federally assisted housing buildings in New York City. And what we could gather from this map is that the highest concentrations of relatively high and very high vulnerability are clustered throughout the South Bronx and in central Brooklyn, with additional pockets in Upper Manhattan and across Southeast Queens. Next, looking at pre-1960 housing concentration in Phoenix, we saw through this map that the highest concentrations of older housing stock was throughout central Phoenix, as well as areas along the Glendale corridor. Next, looking at low-income housing in Miami, this slide focuses on how vulnerability relates to low-income patterns. And what we saw here is that the highest concentrations were located in downtown Miami, as well as in Little Havana. And finally, target tenant type in Los Angeles. This map showcases that family designated federally assisted housing buildings made up the dominant category in Los Angeles, but we could also see elderly and a combination of elderly and disabled housing clusters across downtown LA, Long Beach, and Beverly Hills. And this is a national screening map that visualizes the heat vulnerability index across the US. So just looking at things on the national scale, what we found from this is that central Arizona and areas in the inland southwestern corridors had the greatest clusters of very high heat wave risk, as well as the deep south containing widespread clusters of elevated heat vulnerability. And now moving into the development of the composite heat vulnerability index score, we wanted to normalize each variable onto a common 1 through 5 scale. So how we did this is heat wave risk was converted from ordinal classifications to a numerical 1 to 5 scale. And pre-1960 housing percentage and low-income housing percentage was grouped into percentage ranges and then similarly converted to a 1 to 5 scale. So once normalized, these 3 variables would be able to be averaged across the different metropolitan areas. And then looking at the equation on the bottom right, we could see that this is how we are able to get to our heat vulnerability index score. So just going across these different variables individually first, what we found after normalizing the variables for heat wave risk is that Phoenix ranked the highest by far with a score of 4.9, which reflects the city's extreme desert climate conditions, followed by New York, and Los Angeles ranked the least. Next, going into the pre-1960 housing percentage, this chart showcased that New York City and Los Angeles ranked the highest, followed by Miami and then Phoenix. Then for low-income population, we saw that all 4 of the metropolitan cities ranked above the United States national average. And lastly, going into the merged comparison of the composite heat vulnerability index score, what we ended up finding is that in the end, New York City and Phoenix recorded the overall highest combined vulnerability scores, while Los Angeles and Miami, they remained relatively elevated, but around the United States national scale. And now we're going to move into our next climate risk, which Olivia will cover.
All right, so I took a look at some of the coastal flood risk variables from our data sets. The guiding questions that we aimed to see if we could answer or investigate for flooding include these listed here. So first, are public subsidized housing units disproportionately located in high coastal flood risk areas? Do high-risk tracts have significantly more affordable housing units than low-risk ones? And what is the expected loss of these affordable housing units due to coastal flood risk? And yeah, so the risk focus is building value loss and expected economic loss. Other vulnerability factors to take into account is that economic barriers, including housing affordability, prevent some residents from moving to higher ground. So here are the selected variables of the flooding risk data that we chose to look at in this study. We did have a difficult time, just as a side note. One of our challenges was selecting. There were like dozens of variables, and choosing which ones we thought would be most interesting and most impactful was a challenge. But I will just talk about these four here. So all of these actually came from the National Risk Index provided by FEMA. So the first one is Coastal Flooding Hazard Type Risk Index Rating. And this is essentially FEMA's hazard risk score. It is at the census tract level across the US. Their formula comprised of expected annual loss, social vulnerability, and community resilience. This overall provided us with a qualitative, unit ranging from very low to very high. Our next one is also a qualitative unit, also ranging from very low up to very high. And this is the historic loss ratio. Historic loss ratio, or HLR, represents the estimated percentage of the exposed building value expected to be lost due to coastal flooding. And the third variable that we looked at was expected annual loss rating. Once again, this is another qualitative unit. So what it's telling us is, per the property is expected annual loss very low up to very high. EAL represents the community's average economic loss from coastal flooding each year. And it's an estimation modeled in 4 different subtypes. So first is sea level rise and high tide flooding. Second is 100-year flood area. Third is 500-year flood area. And 4 is hurricane surge. And then the final flooding variable we looked at was the impacted area. And this represents the total area measured in square miles that is exposed to coastal flooding within the specific property. So next, what I'll show you now are a selection of exports from ArcGIS from our tool, just showcasing some different layers. And what I aim to do was actually I picked New York City and Miami as 2 focus areas to make compare and contrasts. So the first thing I'll present is the overall hazard type risk index rating from FEMA. This is New York City, and the key down here is small, but basically greener dots is a lower risk score. The orange and red are higher risk score. And what we can observe from here is the highest rated risk index affordable housing properties in New York City are located in Coney Island, Williamsburg, Prospect, Lefferts Gardens, and Throgs Neck. You can see there is some, maybe you can't, but that red dot is somewhat of an outlier. It's not directly on the coast, although I guess all of Brooklyn is considered coastal. We found that property is 150 Hawthorne Street. It is part of like the affordable housing lottery. And basically what we incurred from this is this risk actually includes like storm surge. It's not just like specifically flooding on the coast. It's a combination of different factors. So it might be due to like a higher social vulnerability or just some other higher weighted factor in that overall score. Okay, this is that same layer in ArcGIS, just now we zoomed in on Miami, which is also a high-risk metropolitan area in terms of coastal flooding. So here it's a bit more dispersed. Affordable housing properties are not clustered and they're actually spread across the metropolitan area, and Dante kind of touched on that before. And we also see in terms of the hazard risk type index rating, moderate and high risk ratings tend to be located closer to the Miami River. So that is right around there. So those orange dots around there. Okay, here is taking that risk score from the data sets. We filtered it by those 4 cities, and then also took the national average. And this is the overall results. So as expected, Miami and New York City do have higher risk scores compared to Los Angeles, and Phoenix actually had, amongst the affordable housing units in Phoenix, they all had a risk score for flooding of 0. So that's plotted here. And then the national average you can compare against is 1.95. Okay. The next set of maps that I want to show, I won't go too deep into them, but it's the historic loss ratio and the expected annual loss. So first, if we'll look at historic loss ratio for New York City, the key findings we have here is that it's low to moderate across most of the New York City area, although there is a somewhat high historic loss ratio clustered in the South Bronx area. Right where it says Bronx at the top is kind of the only place we saw historic loss ratio to be greater than moderate. The total properties we see here with moderate to high is 89 units. However, when we then looked at the layer of expected annual loss, we saw an increased risk ratings for expected loss across all units in NYC. The total properties with moderate to high now increases to 107. To do that same comparison on Miami, now we're looking back again at historic loss ratio. Actually, 0 affordable housing units here have a historic loss ratio greater than relatively moderate, and only 2 properties is made up of that. However, again, now we're looking at expected annual loss. There is increased ratings on every unit. The total properties with moderate to high goes up to 68 from 2. And just to kind of summarize that, it is, again, what we expect. We expected annual loss to be greater than historic loss ratio because HLR tracks past damages while EAL estimates future yearly economic impacts. And this often does show higher figures due to rising exposure and climate factors. In this chart, we're also comparing Miami to New York City. Miami is the blue line and New York City is the green line. So maybe from here we can see for affordable housing units in Miami, they are at a greater increased risk for expected loss. Okay, finally for flooding, here is kind of the methodology of how we calculated our overall hazard risk score. Basically, I picked 3 of those variables: historic loss ratio, expected annual loss, and the impacted area. I also normalized all 3 of those factors. The qualitative ones I normalized on a 0 to 5 scale, whereas the square mileage I normalized using a min-max value score between 0 and 1. From there, I gave each of these a relative weight, and those were, relative scores. So 0.4 weight to historical loss ratio, 0.5 to expected annual loss, and 0.1 to impacted area. Basically using that matrix, here's our calculation. Just multiply the weight by the factor and add them all together. We ended up doing this for the entire data set. So at a national level is the output we got. And this maps that output. So once we came up with our hazard risk score, we calculated it for every affordable housing property in the United States. And this is the results. I will note I removed any risk score of 0 because that was most of like middle America. So obviously anything greater than 0 is primarily like along the coast. And this also kind of proves, or it supports our decision to focus on Miami and New York City, because you can see like the higher risk rating is up in the Northeast and then also down in Florida. And lastly, Judy, talk about air pollution.
Thank you, Olivia and Danta. So I focus on the air pollution. So I also choose the variables basically based on the National Ambient Air Quality Standard and also plus the toxic release. I really want to analyze the questions like whether the public housing or subsidized housing is concentrated in areas with elevated air pollutions, and also different housing type or program tenants, whether their distribution follows some patterns, and whether those exposure vary systematically with housing type and tenant type. So initially, I want to choose the factors about the public health, including the asthma or lung cancer, but we couldn't get the whole data set from all those properties. So I choose the life expectancy eventually to analyze the correlationship between the life expectancy and their air pollution, including the PM25 ozone, and also compare them with the overall risk score nationally. So eventually I see that the life expectancy really has a positive correlationship with the toxic release. And for the other three factors, PM25 and ozone and NO2 is similar as the overall risk rating or score is not like very high between them. So this is why I want to choose maybe the toxic release as the give it more weight to get the overall risk score. So I also analyzed the PM 2.5 nationally and visualized the map based on the EGA screen data set. So we can see that at the west coastline, the California state and then the Washington state is on the top rank over all. And then I think maybe this is also, I think comes from the wildfire and also the heating, and this also cross-verify that our literature research that the heating is has a high correlation with the air pollution. So I also use the toxic release as the factor to analyze the general national level to the different state. And we can see that this is different, totally different pattern. Use the PM 2.5 because toxic release always related to the heavy industry facilities or chemical factory. So this map shows the Indiana state is the highest rank. And on the contrary, California here is at the very bottom value. So this is a totally different pattern. And those two analyze, I use the value. So for ozone, I try use the percentile to analyze the national level. So this is the consistent with the PM 2.5 and California still outstanding for ozone. And then that's why we choose the Los Angeles to compare with the other four cities. And as you can see here, Pomona, California is the top rank, almost 99 percentile. And I also analyzed the relationship between the traffic proximity with the ozone PM25 and the toxic release. So this is the line. You can see that the blue line is come from the toxic release. So that is not very related to the traffic proximity, but NO2 is really matters with the traffic corridor. And for the different housing types or tenant type, I also analyze their impaction or their exposure to the different air pollutants and whether they are close to the traffic corridor closer than other housing types. So from the bottom figures, we can see that the public housing has a bigly difference pattern with the other two housing types. So this means public housing exposed to the toxic release much more than the other two housing programs. So I think this also makes sense because public housing always invested by the not invested, like owned by the government agency, and then the buildings always was built from the new construction, so they can select the different site close to the toxic release. For low income, housing tax credit was like sometimes invested or renovated by the private investors, so they can choose the existing buildings close to the traffic corridor. So this also makes sense for the pattern now. And I use the different factors that I analyzed above to try to get the overall risk score for air pollution. So first of all, I used the same weight for 4 different factors. And then I got the image like this. And California and in the middle of state, they have the higher rank for the overall risk score. But if I use the different weight, if I add like more weight to the toxic release, because that's like highly related to the life expectancy, and then we can see the different pattern, and then California will just drop down from the second rank to maybe like 5th or something like that. So go to the urban scale ozone. I also analyzed the ozone score compared to the national average score. We can see that New York City and Los Angeles and Phoenix, they have more ozone exposure than the national average national level. So this is kind of surprised me because I thought New York City maybe is higher than Phoenix. And also filters, I have some filters for the PM 2.5 with the different risk score and with the different traffic proximity. And even though I filters for the East Harlem, I think New Haven, that area, we can still see that PM 0.5 exposure here. So I think for those areas, the traffic is not the mainly contribution to the New Haven area. So we also can see some data from the other heating and flooding map. That area is actually extreme exposure to 3 kind of different hazard. So I also go to the toxic release. So New York City here, so the color means the highest rank to expose to the toxic release. And I filtered the map in the different housing program, and in Section 8 is really close to the toxic release. The 4 cities, they also, I mean, compared to the national average score is kind of lower than the national one. So to conclusion, the air pollution indicators, we can see that based on those analysis, so those 3, the top image is the overall analysis from all those analysis from the previous slides. And I also include some household here. And the blue bar is for public housing. And for the bottom of the image, you can see all those 3 different air pollutants. Public housing shows the most exposure to the 3 kind of pollutants. And especially for toxic release, they have much higher percentile of 56. So this is also consistent with the national levels public housing problem. And for elderly household, we can also see that public housing has a higher exposure than the national average level. So for family household, we know that a lot of children in this kind of household. So this is very important to analyze the environment risk for children. And that's basically the whole air pollution analysis. So I want to talk about a little bit challenges and limitation. So as Olivia also talked about, we have limited data set. So when I also want to choose some public health indicators, but I couldn't get from our those three data set. So we have to use some other factors instead. And when we just calculated the risk score, as you can see, like I use the very simple weight research. I use like equal for every pollutants. And even I just want to elevate the weight for the toxic release, but I have not like, deep into more research to how those air pollutants have impact on the public health. And the third one is when we just try to layer the different hazard layers in the ArcGIS, and then it's not that very simple to get the readable map. So we can only use the filters to get some like interactive map. But even though we have some limitation or something like that, but I believe that this is raise questions about how vulnerable populations are spatially distributed with the cities and the regions for those three hazard categories. And I believe this GIS map and our analysis could be a solid support for the futures public housing site selection or the other program type selection. And as you all know that our new mayor, Mandani, he's trying to launch more public housing. So I hope this could be a base or a evidence to show him that we can make a difference for the site selection in future. And lastly, I want to express our appreciation to Yana and Catherine. And actually, Yana did the most difficult technical part, and she merged all data set in one Excel sheet for us to use. So yeah, thank you. For now, I'm gonna open the floor to all questions and comments.
All right, hi, my name is Ariana Marslin, and my partner is Rachel Aptowitz. She's on Zoom. And our capstone presentation is an assessment of perceived walkability in Greenpoint, New York. All right, so first we'd like to thank all of our friends and family for being here, whether it's on Zoom or in person. We really appreciate your support. We want to thank Professor Biles for inviting us to participate in this amazing capstone project. And lastly, we'd like to thank Catherine for guiding us through this amazing master's program. We're really excited to show you guys what we've been working on and discuss our results. So our motivation behind this project is to understand how people perceive walkability and compare that to studies that have only looked at walkability through an objective lens. Research studies that focus on objective walkability solely look at the built environment, and it lacks the perspective of residents and the lived experiences. So we want to see how walkability affects quality of life and how it can also be improved. So this is what we will be discussing in our presentation today. So I'll quickly go over walkability and urban sustainability. Then I'll quickly go over objective and perceived walkability. And then we'll go through our methodology, our results, as well as our key findings. So cities are moving away from car-centric infrastructure, which may present as wide roads, narrow sidewalks, and a lack of variability of land use. And they are moving towards sustainable development that meets environmental, economic, and social needs to ensure longevity. So some ways that walkability presents itself in communities, it could be wide sidewalks, green spaces such as parks, parklets, or greenery along the sidewalks, more access to destinations like parks, shopping centers, and public transportation, visible crosswalks, as well as a variety or diversity of land use. So by implementing these changes, it could lead to more of a positive outcomes within the neighborhood. So these are some of the dimensions that it could affect, that walkability could affect. So first, we go over infrastructure. So frequent and better maintenance and upkeep of sidewalks and crosswalks can improve street connectivity and make it easier for pedestrians to get to their destinations. So the second dimension is the environmental factors. So adding more parks, having trees along sidewalks, having parklets, that could help reduce carbon emissions. So the trees could capture the carbon dioxide within the air and help reduce air quality, and also help reduce the urban heat island issue. So the third will be the social impacts. So again, having people outside, social and civic engagements will increase. People will start to get to know their neighbors, and that could also help improve some engagement with local government. And there could also be a better sense of safety. So knowing who your neighbor is, knowing the people within your community, people will develop a sense of safety and trust of their peers and their neighborhood. Another dimension would be health. So again, having people outside be more inclined to do physical activity like walking, running, especially when the environment is comforting, it's attractive, and it is safe. And also, as well as the implementation of bike lanes can lead people to want to start biking more to their destinations, like to work, home, outings. And that could, help them be safe in terms of riding on the street adjacent to people who are driving. And the last dimension that walkability can affect is economics. So local businesses could see more profit within their business because of the amount of foot traffic that could be increased when there is infrastructure that supports pedestrians. So now I'll go over objective walkability. So the EPA developed the National Walkability Index basically to measure the relative walkability of communities. So every block group is assigned a score based on measures of the built environment, such as intersection of density, proximity to transportation stops, and diversity of land use. So they are scored by 4 categories: least walkable, below average walkable, above average walkable, and most walkable. So some of the limitations of objective walkability is that there are only 4 categories. So that can lead to an overestimation of the assigned block group. So there could be blocks that kind of fall in between and is not labeled correctly. It could be labeled above average, but it could actually be below average when you go and actually look at it. It also lacks the lived experiences of residents and underestimates the local infrastructure. So not going out and asking residents what they actually think about their own neighborhood could be a limitation, because if there is a sidewalk or a block that is labeled above average walkable or most walkable, residents might have a different view. This sidewalk or block could be next to a major roadway, or it could be not properly maintained. And to residents, that might not be the most desired way to get to and from their house or to their desired destination. So it lacks, lacks the lived experiences of the residents and doesn't take into account the actual infrastructure that is presented there. So perceived walkability is the opposite. It focuses on the lived experiences of residents to get a clear picture of what it's like to actually move through their city. So it highlights important aspects that objective studies overlook by involving the people. So, considering attractiveness, safety, and comfort. So some of the strengths for perceived walkability is that it actually addresses the real problems in the neighborhood. So again, asking the residents how they feel about their neighborhood will give you the real and raw answers of what is going on, how they experience their life, and how they experience mobility throughout their community. So getting these answers and asking the residents could lead to more safety and improved mobility throughout the neighborhood. So again, having these real problems can actually result to real solutions that could help people. So for our specific research project, our case study selection was Greenpoint. So Greenpoint was selected because it showed some variability in objective walkability scores. It also is a neighborhood that represents the recent trends of other neighborhoods in Brooklyn, where there's a strong history within the area, but there are trends of gentrification happening. So Greenpoint is located in northern Brooklyn, and it is surrounded by Williamsburg, the East River, and Newtown Creek. Population is about 39,000, and the demographics is 70% white, 20% Hispanic, and 7% Asian. So originally, Greenpoint was known for being a very strong working class immigrant community. There was a very large Polish immigration and a large Polish American community. It was also a major industrial hub for shipbuilding, printing, oil refining, and glass making. So in the early 2000s, there was a rezoning for Brooklyn's waterfront that included Greenpoint, and this gave way for development of high-rise residential buildings. So investors were able to turn old industrial buildings to residential and mixed-use development, which created more housing, there was access to the waterfront and more commercial opportunities. So this rezoning kind of gave way for young professionals to move into Greenpoint and start the trend of gentrification happening in that neighborhood. So today, in terms of transportation, Greenpoint has only one line, the subway line that goes through it, which is the G line. And there's only two stops that stop in Greenpoint, which is Greenpoint Ave and Nassau Ave. There are a variety of bus routes as well as a ferry station that will be able to take Greenpointers to Manhattan. But there is still a lack of access to different neighborhoods and boroughs within the neighborhood because of the fact that there is only one line and there is only two stops within Greenpoint. So this is the objective walkability study in Greenpoint. So the EPA National Walkability Index classifies the majority of the tabulation areas in Greenpoint as above average walkable or most walkable, with only two tabulation areas being classified as below average walkable. So this map kind of shows, or you can really infer when you're looking at the map that Greenpoint is walkable with the exception of the two blocks. So with our study, we kind of wanted to go around, ask Greenpoint residents how they feel about their neighborhood, how walkable their neighborhood is, and look at our data and compare that to this map to see if there was any changes, anything that stayed the same, and whatnot. So this was actually our first tour around Greenpoint before we started doing our survey. So we were able to do the nature walk that is conveniently across the Newtown Creek treatment plant. We were able to see the waterfront, which is being, that has high rises being developed there currently, and we can get a sense of the gentrification that is happening in that area. But we were also able to see the Polish influence that is still alive in Greenpoint. There was a Polish bank, a lot of Polish bakeries and restaurants there. So very diverse community, but again, we were able to see, the gentrification that's happening, as well as the strong history that is still present in Greenpoint. So this is how we decided to recruit our participants. So first we had our online survey. So the survey was through the ONA data platform, and it took people around 15 to 20 minutes to complete. And then we also did Facebook ads to reach the residents of Greenpoint through their social media. So we were able to put Greenpoint's zip code in to reach, to have these ads show up when people open, Facebook, Instagram, things like that. And then lastly, we did some outreach. So we had emailed a bunch of environmental and community organizations within Greenpoint. And we were able to get in touch with the Greenpoint branch of the Brooklyn Library. They had a clothing swap that was happening. So we were able to table there, pass out some flyers. We also went to Greenpoint Spring Market to pass out flyers to people who were walking in and out and getting to talk to people on the street who lived in Greenpoint, asking them about their opinions on the neighborhood. And then we were also canvassing outside of subway stations, passing out flyers, trying to get people coming back from work, which was around like 4 p.m. So we can, one, ensure that we got participants who actually lived in Greenpoint, but we were also able to talk to some people and get their opinions on our survey as well as Greenpoint itself. So these are the different sections of our survey. So first we got the consent and eligibility. So a lot of our all of our participants needed to be over the age of 18 years old. Then we asked them about their demographics, so age, race, and ethnicity. Then the bulk of our research data came from the questions about Greenpoint and their how walkable it is. So we asked them about to perceive their home, their block where they live. So we asked them about transportation access, traffic, noise, and safety. And then we gave them 3 images of streets that they live near. We asked them for quality, accessibility, land use, and attractiveness. And then we gave them 5 random streetscapes all around Greenpoint, and we asked them to give us qualitative descriptors of those streetscapes. So here are some of the examples of the questions that showed up on our survey. So again, we asked people to perceive their home block. So the first question would be assess the block where you live in terms of traffic. So they could pick excessive traffic, a fair amount of traffic, some traffic, but not too congested, little traffic, very little traffic. So that's how those questions went for when they were perceiving their home block. And then moving on to the next section was the 3 images of blocks that they live near. We used a Likert scale so that they can evaluate the image. So for this image on the slide here, we had them assess the quality of the street and sidewalk infrastructure. So they had a Likert scale of very poor quality and excellent quality. So they were able to pick between that. And then lastly, with the 5 random streetscape images across the Greenpoint neighborhood, we gave them 5 they were able to select up to 5 characteristics to describe the street and the sidewalk of the image. So some of the descriptors that were available: accessible, boring, chaotic, desolate, diverse, impersonal, intimate. So these were some of the qualitative descriptors that they were able to pick for those 5 images that they were given. So now I'm going to pass it off to Rachel to talk about our results.
Okay, good morning, everyone from sunny San Diego. Thank you to my team for doing the bulk of the in-person outreach for this project while I moved across the country. Now I'm excited to take you through the results of our survey. So first, I'd like to summarize the characteristics of the survey participants who responded. Overall, we had 29 total Greenpoint residents that were over the age of 18 who responded to the survey. The majority of our participants were between 25 and 44 years old. Younger participants were slightly overrepresented, and we weren't able to capture as many of the older residents of Greenpoint. Our respondents had diverse responses from across gender identities. White participants were overrepresented. We asked participants if they had any sort of mobility limitations because we thought that might be a factor in perceived walkability, and we did get some responses from participants with mobility limitations. The majority of the survey respondents lived in Greenpoint for less than 20 years. So we were hoping to capture some of those longer term residents who have seen the neighborhood go through these dramatic changes. But younger and newer residents of Greenpoint were slightly overrepresented in our results. Of the folks who responded, about half of residents utilized public transit as their primary means of transportation, and half use walking or biking as their primary means of transportation. So a nice diverse use of transportation already by residents in the neighborhood. We do believe that folks who primarily use single passenger vehicles who drive around Greenpoint were underrepresented, especially because when we were ourselves walking around the neighborhood, we saw a lot of passenger cars parked along residential streets. Next slide. This map shows where participants lived. So they were able to select a 200-meter hexagonal area within the neighborhood. And that gave us an approximation of their exact address. We saw kind of a cluster of participants in the northwest portion of the neighborhood. So kind of left of McGinnis Boulevard and north of Greenpoint Avenue, that upper left quadrant of the two major thoroughfares that cut through the neighborhood. And then we saw what looked like a cluster of respondents in the southern portion of the neighborhood near Meeker Avenue, which runs below the BQE Brooklyn Queens Expressway, which cuts off the neighborhood to the south. We were glad that we got responses from many different areas of Greenpoint, but due to the overall relatively low response rate to the survey, many areas of Greenpoint didn't receive responses from any residents. So our results will really focus on the areas where we did get direct responses and perceptions of lived experiences of residents. Okay, so now I'm going to take us through the results of what residents ranked as their perceived walkability of their neighborhood. Overall, Greenpoint respondents had a very positive perception of walkability, especially when we asked them about how they felt about their exact block. So in this map on the right, we can see a lot of that light green color above average walkability and that dark green color respondent saying that their block is most walkable. There was one respondent who appears to live very close to Meeker Avenue, who, based on their perceptions of walkability along the dimensions we asked about, their overall score was calculated as least walkable. Next slide. Okay, so although overall respondents had a very positive view of walkability, we want to dive into the different dimensions of perceived walkability that respondents gave us their opinion on. So going from the really dark green positive perception on the right of the graph towards the lighter green, more negative perceptions on the left of the graph, we can see that this first dimension, proximity to parks, recreation areas, and green spaces, respondents felt most positively about. So they definitely feel that their block is close to green spaces. We also saw that respondents felt that their proximity to public transit, that they're very close to different transit options, as well as they perceive a very positive overall perception of safety on the block where they live. Respondents felt a bit more moderately about access to shops and services as we start to look at this medium value on this Likert scale, getting into the kind of lighter green range. And then these last two dimensions is where we started to see some concerns. So survey respondents had a more moderate or even starting to see a negative perception of the overall amount of noise and traffic on their block. Next slide. Okay, this next part of the survey asked respondents to take a look at those streetscapes. So these are the 3 images of streets near their block, so within about a 200-meter hexagonal radius of where they live. And respondents assessed a total of 75 street images across Greenpoint, across similar dimensions of perceived walkability. So we asked them to evaluate the images in terms of quality of street and sidewalk infrastructure, the overall accessibility for pedestrians and cyclists, their perception of the diversity of activities within those images, their overall perceptions of noise and safety, and the overall attractiveness of the street and sidewalks seen. And these would be areas that respondents would be very familiar with since they're very close to to their home address. Next slide. These are some of the streetscape or sidewalk images that respondents were able to evaluate. So we looked at hundreds of images from Google Maps, and we selected 3 to 5 images for each area of Greenpoint that we felt were representative of that specific section of the neighborhood. So you can see some images have a lot of greenery. Some have, very visible bike lanes in that area. Some have very attractive views of Manhattan across the river, this image all the way to the right. And then others perhaps would be considered more desolate, more commercial or industrial pockets of Greenpoint, more space for cars than pedestrians. So really giving respondents a diversity of images to react to. Next slide. And these were the results of respondents' perceptions of Greenpoint streetscapes. So again, the same Likert scale as the previous graph. We can see at the top of the graph, overall, the dimension that ranked the most positively was the perception of safety of streetscape images, the quality of street and sidewalk infrastructure, and the overall accessibility for pedestrians and cyclists. More moderately, the overall attractiveness of the images that respondents assessed. And then again, we see the perception of noise coming up as a concern for areas near where respondents lived, as well as the overall diversity of activities and use of space. Next slide. So we took those results and translated them into another map of perceived walkability scores across Greenpoint. And for the data that we received from this section of the survey, we can again see that overall Greenpoint streetscapes were ranked as above average walkable or being amongst the most walkable. So still a lot of light green and dark green dots on that map to the right. But respondents reacted to streetscapes in a more varied way than the specific scores of the blocks where they lived. So we can see that there were now a significant number of streetscapes that were rated as below average, that orange color, or even amongst the least walkable, the red dots. And this result really suggests to us that residents perceive greater variability in walkability from street to street. So someone might view the block where they live as being really highly walkable, but then turn the corner and encounter a street that feels much less walkable. Next slide. And this is to give us a sense of what streetscapes were ranked more favorably and what streetscapes were ranked as less walkable. So this top right graphic was one of the dark green dots, so amongst the most walkable blocks in Greenpoint. We can see greenery, we can see a protected bike lane on this street, a nice diversity of residential uses. And then in comparison on the top right, we can see a block or a streetscape that was ranked as least walkable. So this is a dot which looks like an image coming off of the off-ramp of McGinnis Boulevard. So, I would think that residents who've encountered this street would perceive this area as particularly noisy since you're coming off of the Pulaski Bridge. Next slide. Okay, so taking all of our results of perceived walkability, we then wanted to go back and compare it to the objective walkability indexes in Greenpoint. So going back to the EPA National Walkability Index that Ariana introduced previously, again, Greenpoint has 26 neighborhood tabulation areas. These are units based on US Census data. Within each of these areas in Greenpoint, the majority are classified as highly walkable. So pretty much dark green, light green across the neighborhood. We then wanted to translate this index into a scale of the study of our results. So we compared the National Walkability Index with our perceived walkability scores by overlaying the hexagonal units that we used in our study, and then assigning each of the 25 200-meter hexagonal units used for perceived walkability analysis their average National Walkability Index value. So those 25 hexagons on the right are the objective walkability scores in Greenpoint based on the EPA National Walkability Index. Next slide. And then we sought to create a composite index using all of the results that we received from survey participants on their perceived walkability of different areas across Greenpoint. So we took all of the observations of respondents' evaluations of their own block, so those 29 perceptions, as well as their perceptions of the walkability of Greenpoint streetscapes, so areas near where they live. And we had a total of 101 observations, so that was our overall sample size. And then we created a composite index of their overall perceived walkability score based on these neighborhood tabulation areas. So we can see in the resulting graph on the right that there was a range of perceived walkability across Greenpoint neighborhood tabulation areas. So we see, again, mostly that light green, but we see some orange areas and also some red least walkable areas. Next slide. Okay, and here is where we finally got to our overall comparison that we set out to see at the start of this research 2 semesters ago. So we can see on the left the objective walkability scores of Greenpoint, and on the right are the results of our research, the perceived walkability index that we created in Greenpoint. And then we went hexagon by hexagon and were able to compare between these 2 different measures. We can see that for 15 of the hexagons, there was no observed difference between objective and perceived walkability. However, within 10 of the neighborhood tabulation areas, perceived walkability scored lower than objective walkability. And the differences between objective walkability based on the National Walkability Index and perceived walkability based on the survey responses, the data we gathered in our research, were statistically significant. Furthermore, in comparison to the map of objective walkability, the perceived walkability map shows much more variability. So we can see, for example, one 200-meter hexagonal area defined as least walkable, that one bordering Meeker Avenue, the red dot, bordered by 2 hexagons that are light green, so evaluated as having above average walkability. In general, these perceived walkability scores are capturing granularity within neighborhood tabulation areas from street to street and really identifying which parts of a neighborhood are perceived as more or less walkable. Next slide. Okay, just to summarize all of the key findings that I just went through, overall, Greenpoint residents had a really positive perception of walkability on their block. Their biggest concerns were around the dimensions of traffic, so a little too much traffic, and noise, a little too noisy. Residents also had an overall very positive perception of walkability of streetscapes near their home. However, again, the concern around noise came up, and the diversity of activities and use of space was also a weak dimension. Another key result was that overall perceived walkability was significantly lower than objective walkability indexes. And residents perceived more variability in perceived walkability than objective indexes. Next slide. Finally, we wanted to make some recommendations for future work. So based on our research, based on the survey responses in the locations assessed by residents, efforts to improve walkability in Greenpoint should focus on decreasing traffic, decreasing noise, and increasing the diversity of activities and use of space. Those last two dimensions will definitely need to be balanced. Perhaps if there's more activities going on, there might be more noise and vice versa. And then our overall research really suggests the importance of measuring perceived walkability in addition to these more traditional objective measures. By assessing perceived walkability alongside conventional measures of objective walkability, policymakers and city agencies can better pinpoint specific areas and dimensions within a neighborhood that should be targeted to improve walkability and really take into account the lived experiences of residents. Thank you so much.
Thank you, guys.